Hello there, Math 126 fans. Going to talk about global max and min questions. Students really get bogged down in these. They think, oh, there's so much going on. And so I'm going to show you some visuals. I hope make it very clear. I think a lot of it boils down to this general 3D confusion, which is you are given a surface. That's your function. This is all of chapter 14 and 15, an issue students have to deal with. Separate from that, you're given a region on the ground. And in this case, the region looks like this. And that's this picture here. And the question is asking you, where should you stand so that when you look up, the distance to the top is maximum? And where should you stand so that when you look up, the distance is minimum? And the principle is, it has to either be at a bump in the middle or at an endpoint. The problem is there's a lot more endpoints. Your job is this, and it becomes very clear after I show you some visuals in a second, but your job is to study the endpoints on each side. That's why these problems can be long. So let's call this 1, 2, 3. So I train students up that you just want to make your solutions as clear as possible, that you've analyzed all the points on side 1, you've analyzed all the points on side 2, you've analyzed all the points on side 3. You don't want the person grading to have to search to see that you actually did that. And then you're going to analyze if there's any bumps on the inside, properly inside. Are there any critical points? So unfortunately, this is 3 small problems. I'm going to show you visuals of this in a second, because I think that'll hit it home. But you just need to describe the size. What does it mean to be a point on the edge here? Well, what do all of those points have in common? What they have in common is that x is 0. So you say that in order to be on that first side, x has to be 0. So the picture is very important. And y has to be between 0 and 4. We would like to plug all of those points into our function, but let's get to that in a second. What about on 2? What do all those points have in common? Well, what they all have in common is that y is 4 and x is between 0 and 2. So you can see how I'm just describing what it means to be on our sides. The last one is more interesting because it's a line. How do you find the equation of a line? Sometimes students ask me to review this. The equation of a line is 4 minus 0 over 2 minus 0, which is 2. And the y-intercept is 0. So if you're on this side, you have y equals 2x. So if you have a point on here, you're going to have x and 2x is one way to say it. X is between 0 and 2. So I encourage students to sort of, before they even start the question, to itemize what the endpoints are. Unfortunately, there's a lot of them. Now, for each one of these now, we can solve a one variable calculus problem. Now, if you don't know how to do one variable calculus, this problem becomes much harder. But what I'm saying is, first I'd like to know what happens when x is 0. Ooh, that's kind of nice. When I plug in x equals 0, any of these points, I just get 9. So it's a constant function on that side. Let's keep going. What about when I plug in a 4 for y? Okay, if I plug in a 4 for y, what happens? F of x comma 4. Well, that's going to give me 4x squared minus 4x plus 9, because I just replaced that with a 4. Lastly, what happens when I replace y with 2x? Well, that's going to give me the following. F of x comma 2x. And I know at this point, I can't do that. I give up. Don't give up. I tell students, if you just write all this is going to be simplified a little bit. I'm going to give you most of the credit. So you need to talk to your instructor, but I tell students, this is how I grade. Is the one variable function above the first side there? Is the one variable function above the second side there? Is the one variable function above the third side there? If those are all there, I'm already going to give the students lots of credit because they're showing me that piece. Now, what we need to do with each of those, let's talk about here in just a moment. But the others, I just want to kind of lay out what needs to happen. And after you've seen a couple of these, you're like, oh, I can see like almost the entire solution laid out from the beginning. So let's talk about the inside. The inside is, what if I do the partial with if I find the critical points? So let's zoom out a little bit so I have more space to work with. Partial with respect to x this is just studying if there's any other points I need to consider. Minus y is 0. The partial with respect to y is minus x. This implies x is 0. If I plug that in here, that implies y is 0. So equation 2 gives me this. Plugging this into equation 1 gives me y has to also be 0. So there's only one critical point. It happens to be right on the boundary. And so you can plug that in. The end of every global max and min question involves plugging into your original function. So if you were unsure if you needed to consider this, you could just plug it in and say, oh, this corresponds to z equals 9. Okay, that's the layout of these questions. What do you then do? Well, for each side, you then have a one variable calculus problem. Now on this side, every single point corresponds to z equals 9. So you don't really have to do more analysis there. For the other two sides, we have stuff to do. Like for this one, you would say, well, I know that the maximum of a one variable function has to occur at the endpoints or at a critical number. How do you find the critical numbers? You take the one variable derivative, set it equal to 0. From that, you get x equals 0. And you plug in x equals 0 and x equals 2 here. So basically, we're learning that there's 2 points we have to consider here. We've actually already plugged in 0 and got z equals 9, but we also need to plug in 2. This is the part where students get mixed up. They're forgetting their one variable calculus. In one variable calculus, the maximum of a function is either at an endpoint or a bump. Okay, I think now is a good time that I show you some visuals. Here is this visual. I always show this in class. That's what we're studying. Now the surface itself goes on forever. It looks like this. But the question was saying, and the surface itself only has one critical point, and it's a saddle point right there. So the surface itself doesn't really have any bumps. Okay, we could have done that analysis, but the question didn't ask us. The question said, I only want you to consider above that triangle. Okay. Now, it's not easy to make these pictures. I had to work hard at it during the pandemic. What we just did is we went side by side and we looked at what happened. So first we said, what happens if we plug in? So we said, forget the inside for a second. What happens when we plug in x equals 0 to our surface? We get 9. Not only is it 9 at the endpoints, it's 9 everywhere on that side. So on that side, the maximum is 9, the minimum is 9, it's just 9. That's what we found first. Then we went to this other side. We did this side next. This side doesn't have any bumps in the middle either. If you just think about that as a one variable function, let's get rid of everything else. That's what's happening above that far side. And the minimum is here at 9. And the maximum is here, I think it's like 17 when I plug in that point. So far we've analyzed those two curves. One of them was 9, one of them was a parabola. Are there any other points to consider? Now the other side's the one interesting side, because you can see not only does it have, let's get rid of all the other things. You can see above this side, it has a high point here and a low point in the middle. How are we going to find that? Let's go back and look. So I always like to show that because I think that starts to hit home, right? On each side, we should be thinking about the endpoints and are there any critical points? But this was always 9. That was no big deal. Here, the only critical value we got was 0, which already is an endpoint. And when you plug in 2, you get that 17. Once you have finished analyzing each of the sides, you're going to have a collection of points, and you're just trying to see who wins. So currently, we've done this, we've done that, we've done this. There's only one thing left to do. which is we're going to plug in 0 to this and get 9. We already know that value. We're going to plug in 2 into this, and you're going to get 17 because you're going to get this matching up. So the only thing left is there any other point on this side? And we know from my visuals there is some point on this side that matters. How do we find it? We take the one variable derivative, 8x minus 4. We set it equal to 0. We get x is a half. That's the answer. So we need to plug in x equals half. Now, you can do one of two things. You could go back and say, well, if x is a half and y is 4, I now have the precise coordinate here. 1/2, 4. And you could plug that back into your original function. Or you could say, well, I already plugged in 4 here, so I'm just going to plug in a half right there. That's also fine. Does the same thing. If I plug in a half here, I get 1 minus 2. So 1 minus 2. Z is 1 minus 2 plus 9. So it's 8. So Z is equal to 8 here. It's equal to 9 all along here. Everywhere here Z is 9. And right here Z is 17. And it's got to be one of those. There are no bumps in the middle. There's no critical points inside the region. Just that one point on the edge, which happens to be a saddle point. We already know the value is 9 there. And there's no other bumps on any of the sides. So that's what we're doing. I know it's kind of a bit to think about, but I hope that explained it to you. But you just need to know the process of look at one side. You do that by just describing what it means to be on the side, plugging it in. Look at the next side. Look at the next side. Done. The minimum is 8. The maximum is 17. You got to see another one. And that's why you did a few in the homework. So here's another one, straight from another one of my old exams. So again, on this one, the maximum is 17, the minimum is 8. And you can see solutions on my recent exam. But now that we've seen the process, I think this is one of these things that slow the first example. It's still kind of slow the second example. And then after that, it should be fast. What I mean by that is, here I have this function. You can do the partial derivatives right from the get-go if you want. That's fine. So let's say we do the inside first, the partial with respect to x. And what I tell students is, even if you're confused by that, hopefully you're starting to see there's just a ton of stuff you can do. I sometimes say this is a problem that's hard to leave blank. So you're going to set this equal to 0, set this equal to 0. X has to be 3. Plugging that in doesn't change anything in the first one, so your only critical point is 3, 0. So we'll just plop that to the side, and so we'll have to think about that in a little bit. Now the rest of the problem becomes trying to plug in all the endpoints. It's just there's a lot of them. Okay, so we're going to graph x equals 4. There's x equals 4. Where am I getting that? They told me that. I'm going to plot y equals 0. That's right here. Success. I'm going to plot y equals x squared. Right there, y equals x squared. Okay, so now I can see the region, and I can see the boundaries. There are 3 boundaries, and I would like to study what it means to be on their sides. So now when you see the second time, like I said, it should be starting to get faster, what we're seeing. Okay, so one by one, I'm going to describe what it means to be on the sides, and it doesn't matter the order. So let's talk about if you have a point on this side, on this edge, and you plug into the surface. What do they all have in common? They all have in common that y is 0 and x is between 0 and 4. It is important you recognize how big and small x can be because those are endpoints. These points are significant, as we saw in our picture. But you need to see if there's anything else to consider. So now we're going to take our function, replace y with 0. Now this ends up being nice because you get z is 0. So now we don't really need to plug in endpoints because now we know everywhere along this side at every single point z is 0. So we're done with that side. And z equals 0 currently is our only candidate. Okay, let's keep going. What about if you're on this side? Well, then x is 4. It would be nice to label this point, as I know it's significant. If x is 4, then y has to be 16. So 4 comma 16. So y is between 0 and 16. What happens in our function if we replace x with 4? Let's see. Let's put in a 4 there. We get 3y minus 4y. We get minus y. So here's where I start to see where students, if they understand their Calculus 1. Calculus 1 says the maximum of a one variable function occurs at a place that's either an endpoint or a critical point, or we might say critical value. So I'm going to have to plug in 0, but 0 we already know what's going to happen. It's going to give me negative 0 or 0. I know I need to plug in 16. That's one of my endpoints. That's going to give me negative 16. But are there any other points in between that I need to plug in? Well, in order to check that, I could take the one variable derivative and set it equal to 0. And then you go, hold on, that never happens. That's good news. It's good news if you don't get any one variable critical values, because that means you are done. That never happens. Okay, so now we're down to one last side. What does it mean to be a point on this side? It means that y is equal to x squared, and x is between 0 and 4. That describes a point on this side. I need to plug that into my function, x squared. What happened? So I'm replacing y with x squared. So this is going to become 3x squared. Replacing y with x squared, so this is going to become x cubed. Now I know I'm going to plug in endpoints to this, meaning 0 and 4. But if you plug in 0, you just get 0, 0, which we've already plugged in. This always happens because each one of these corners is the endpoint of two different things. So it's kind of, you've already plugged it in. When you plug in 0, 0, you just get 0. When you plug in 4, you get 4, 16, which we already know is negative 16. So the only question is there anything else I need to consider on this side? And once I'm done, the answer will be sitting here. Currently, the minimum is negative 16, and the maximum is 0. But is there anything else? So now we need to do the one variable derivative, 6x minus 3x squared. Set that equal to 0. This factors nicely, it appears. So it's going to be 2 minus x. So I get two values. X equals 0. That's good. I've already plugged that in. And x equals 2. Okay, that's a new one. So I need to plug in 2 as well. Now, what does it mean to be 2 on this side? Well, if x is 2, y is 4. And that means, let's put a 2 in here. Put a 2 in here. That means you're going to get 12 minus 8, which is 4. So that's the max. And that's the min. So it's one of these things of, if you've analyzed each side, your answer is sitting there. And if a student came to me after the fact and say, why did you take off points? I would tell them, here are the things I must see. I must see this. I must see this. And I must see this. That shows me you analyzed points on each boundary. If you don't do that, you're going to be missing points. I also need to see this somewhere. From there on out, it's a bunch of one variable calculus. Why didn't we do more here? Well, that was just a constant. Why didn't we do more here? Well, there were no critical numbers. Here we actually had to do more. All right, I hope that gives you the process. Again, if you go to my materials page, you can see more examples. If you look at my lecture notes, you can see more examples. But I hope that gave you a plan of attack for those questions. All right.